if you would print that and read that before you come to the lab, we're going to do spectroscopy of greenhouse gases. And so I like to do that lecture as a conversation with you guys and talk to you about greenhouse warming and what science says about it. And yeah, interesting topic is all I have to say. And then I went to Achieve and opened all of the lecture PowerPoints there. You should be able to access them ahead of time. Now, I'm going to make edits to some of them and just be aware that they won't be exactly the same, but just ignore that. Does that work? And that way I give them up, you have them ahead of time so you can print them if you would like to take notes on. Okay? And so that was my remedy since I'm still editing on the group that I'm working on. And I keep forgetting to post those on Campus Web. So I just made them all open, and then, like I said, there'll be a few slides that change. Cool? All right. We didn't even get started on the test corrections. Okay, I'm just going to be bluntly honest. We were trying to get some labs done, and I was working on labs and tests for my quant class, so I didn't get a chance to start on them. And so those will not be included. I won't have them done by midnight. There's just no physical way for me to do that. So I'm going to be honest, and we'll work through them during the next week. All right? Sound good? I was going to try, it just didn't happen. Okay? Any other housekeeping items? Yes?
On the lab, whenever we're doing our calculations for like theoretical percent yield,
Yes.
are we doing calculations for both the base and the acid, or just one?
You can do just one of those. And then remember when you're doing them to use the expected product to do your calculation. All right, and I showed you which one that was. It's on the black slide. It's actually on the other slide also, but it's the one that has the smaller molecular weight. And then that way all your calculations match. Okay? Yeah.
If I did both of them added together, do I have to do that?
No, that's fine. If you did both of them, that's wonderful. It's just good practice. But we'll only look for one of them, the one that you made, but you may not be making that product. But I ask you to do it that way because it makes the grading. If you guys all use the same molecular weight, then it makes my grading a lot easier. Yeah. So. And we really don't know which product you made, right? Well, maybe we do. But. Bless you. Any other questions?
So for the lab, do you want us to copy over our partners' notes from what they made?
I want you to do some observations from both, yes.
Okay.
Okay, always that's the case when we do both of them and what looks different about yours and so on.
Okay.
That would always be the case. I'm just asking you in terms of the calculation that you only have to do that one time, okay? And I had a conversation with my lab assistants who helped me grade that about that already, so, yeah. Cool? Yes, ma'am.
Can you go over how you're doing the Lewis structure?
The Lewis structure is literally in the lab lecture, okay? And so it would start with a benzene ring, and then I want you to go from there. You could show the benzene ring like this, but I want you guys to, all of those structures in there are Lewis structures, okay? The ones that are shorthanded in that fashion, okay? Does that make sense? Yeah. So go to the lab lecture for that. And the reason you also have to go there anyway is because you need the molecular weight for that compound, so you have to do the calculation from that structure. Cool? Yeah. Anybody else? Good question. It's so noisy when I came in and you guys were all gabbing and it was so nice, and now all of a sudden we talk about chemistry and it's really quiet. It doesn't have to be that way. You guys can still talk. All right? I want you guys to, we're going to need it. I'm going to need your help. I want you guys to put the orbital filling diagram on a piece of paper right now so you'll have it handy. So I want you to replicate that for me. We good, or do I need to go back?
You go back.
So, remember, it's just going down on where the gold slashes are at, 1, 2, 3, 4, 5, 6, 7, and then start with a 1S, then add a 2S, 2P, and then on 3 add S, P, and D, and then on line 4, S, P, D, and F, and those just continue on down from there. Okay? And then you just put in your slash arrows going down at angles. All right, we're getting ready to use this, and so I want you to be able to do this on a test too, because I'm going to ask you the same question on a test. Does that make sense? All right. So we worked on energy levels, and then we're going to start writing configurations. Okay. And so write the complete electron configuration for lead. All right, write the complete configuration for lead. So it's going to start with what? You should find lead on the periodic table. Anybody see it? It's right here, right? Yeah. So if I go all the way down to number 82, element number 82, then we're going to use the periodic table to help us. We also have our electron field diagram to help us. But I'm going to start with 1s2, right? Would you guys agree with that statement? What's filled next? 2s2. What's next? 2p6. Now the 2 is full. Where am I going? 3s. Okay, I'm going to let you guys work from there. Is that okay? Just patiently use your electron fill and go all the way down to where? 6, right? And you're going to go across and fill the D, and, well, work on that, okay? Follow your pattern on your sheet. Follow your pattern on your sheet. Only 2 electrons in the S. What's the max number in D? And what's the max number in D? 10. Okay? Max number in D is 10. What about F? 14. So those are max numbers that you have to know, right? How am I doing? Oh, there you go. So it's not painful. Bless you. All right. There it is. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, and 6p2.
What? There it
What?
has. 4F14 in there.
Yeah. It's right down there. See where that star is? That moves up.
So why did you put 3, what is it? 4S before 3D?
4S. Four S fills, then 3D, then 4P, then 5S, then 4D, then 5P, 6S, then 4F, then 5D, and then 6P. And that's the order.
So,
Does this explain why we need this? So you have to identify where it's at and then work through it. Now there is a shortcut, you guys know that, right? That you can start, and we'll learn about that. We can start with the nearest noble gas, and so we would have started with xenon and then filled across from there. Okay, and so we'll learn how to do that also. But when we're doing the smaller elements, this isn't that big a deal. When we get to the elements with more electrons, then it's almost impossible to do without the fill diagram. Okay? So I'm really encouraging you to walk through that. And let's go make sure that now that we've tried this once, we'll try it again. We fill 1S first, then 2S, then 2P, then 3S, then 3P, then 4S, then 3D, 4P, 5S, 4D, 5P, 6S, 4F, 5D, 6P, and that's where we ended with the lead right there. Okay? That's where we ended with the lead. And this is related to energy. Now, then I'm going to tell you that there are some elements, right, that don't behave like this. And the course where we really learn about that is in advanced inorganic chemistry. Okay? And so we'll work through those, but we get to some elements that really misbehave. For example, elements in family 9. And they don't feel like you would expect. Okay? And so there are exceptions to this rule. Cool? All right. So, all right, can you identify the neutral element that has this ground state configuration? Can you identify that? So 1s2 is full, 2s2, 2p6 is full, 3s2, 3p6, 4s2. Calcium. Right? So all of those are full. And so that element would be calcium. Okay. All right, this is kind of fun. I'm gonna do one or two basic ones, and we'll start with beryllium. And all you do, if I'm looking at this, then I would start with the lowest energy orbital and fill appropriately. So I would put the 1s up, and I would throw in the electrons that I would find there. And if you notice, it's also doing the energy diagram over here, right? And it's showing that 1s, and it's got the 2 electrons in it. What would I fill next? 2s. And so when I fill 2s, then I would go 1 and then 2. And so now I have assembled that correctly, and my energy diagram is correct. We also get the dot structure, the Lewis dot structure, right here. It's showing those 2 electrons in the valence shell. And it also gives the electron configuration 1s2, 2s2. Cool? And then I could try another, or I can go up in levels, and so we can do sodium. And so with sodium, I would start in the same place with my 1s, and I'd go ahead and fill that. And then I would put in 2s and fill that. And then I would go to P. Now, I have a quick question. I'm going to put that 1 electron in there, but you guys remember our filling rules, right? And can I put another electron in that orbital, or do I need to put another lobe of P up there to put an electron in it? There can only be 1 until I get the 3 sublevels with 1, and then I go to pairs, right? If I don't do that, let's say I go ahead and throw this one in there, it says you've violated Hund's rule, start over again. Okay, you guys with me? So I violated a rule in my fill. And so then I go to reset, and we're going to start over with sodium. And so this gives you guys an opportunity. And if I drag, six, 7. I don't know which one I put that one. Which one did I put that one in? I put it in C. All right. Yeah, it does. You can look over in the energy diagram and see which ones you put them in. So anyway, so I got those, and I need 1 more electron, don't I? So we'll throw another S there, and then throw that in. Cool, and so then it counts that for you for practice. If we go to level 3, it gets more complex, and we get more electrons and so on. So I'll let you guys play with that. Fun stuff. And we'll go back to the lecture. But that's to practice filling if you need that help. All right, abbreviations, okay? Abbreviations, when we talked about this a minute ago. And so when we pull up our lead, then we can go to xenon, which has the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. And we take all of that and we replace that with the xenon in a box. Okay? Yep, and then we take that last piece from the 5p6, the 6s2, 4f14, 5d10, and 6p2, and we write that as the finish of that. Okay? Noble gas symbols are used because noble gases have full valence shells, completed outer electron shell. All right. How about astatine, element number 85? Can you guys write that? Where am I starting? You guys have your electron fill diagram. Should be the S on that level. And then what fills after the S? F4, F14, and then which D will go 5D? 5D, 10, and then 6P5. Yeah. Because it shortens it. So instead of writing all of this, that's xenon. And so it's accepted as shorthand, so we can cut all that off. So we cut it right there, and we take that and move it past the xenon.
I just mean like, why couldn't we have started at like lead or something? Is there a specific
Because
reason?
that's customary to do it that way.
Okay.
Yeah, to me, yeah, why not? So give the outer shell, and that's all you really should need. But I don't know. It's just not what's expected in terms of that ability. So. All right. As you move away from the nucleus, the energy of the sublevels from different major energy levels overlap. Okay, and this results in anomalous electron configurations. And anomalous are, well, columns 4, okay, 9, 6 and 13, elements there. Well, they don't always behave, and like I said, we'll work on this when we get to advanced inorganic chemistry, but this is giving a couple examples. Now what you notice is that this 4s2 3d4, instead of that we do 3d5. That's a more stable conformation with a single electron in each of those lobes, and then a single electron in the 4s. And so we actually see that shift of one electron into the D, and here we see where a full orbital is more stable. And so where this D10 is full and we have a single electron in the S is more stable, and so unexpectedly it fills out of order. Okay, so there are exceptions to that on the periodic table, or elements that actually defy what I'm teaching you right now. Okay, I'm not going to ask you to know those. Just know that there is discrepancy sometimes, and that's how we also get to sometimes where we have iron, which is +2 and +3, and we're going to look at it here in a minute. And so we're going to do electron configurations of ions right now. And so the atomic number plus the charge for the negative ions, the additional electrons, or the atomic number minus the electrons that are missing for positive ions. And atoms and ions that have the same electron configurations, as I said the other day, are iso or isoelectronic. And so they have the same electronic configuration. And so right now we're going to look at that with fluoride and sodium. And so I want you guys to do the electron configurations for the fluoride ion and the sodium ion. All right. right? Fluoride ion. Fluoride has a total of 9 electrons, right? When we add that minus, we get to 10 electrons. Would you guys agree with that? And so 2, 4, plus 6 is 10 electrons, so that would be the structure for fluoride ion. If I do sodium, right, it's in a plus, so how many electrons does sodium have in its neutral state? A total of 11, right? And so to be positive, I have to lose an electron. So sodium plus has 10 electrons. Would you guys agree with that? And so it's 1s2, 2s2, 2p6. Does that look familiar? Right? They're isoelectronic. What noble gas is the same, has the same electronic structure as the fluoride and the sodium ions? Neon. And so neon's electronic structure is 1s2, 2s2, 2p6, right? And so it's the same. Can you guys do another ion, all right? Another ion that would have the same iso electronic structure as those? What's one? O2. O2 minus, the oxide ion. So it would be the same. There's a whole series, right? If I went to N minus 3, it would have the same structure, right? You guys with me? So nitrogen would be in that same family. All right, if I go to magnesium and do the same thing there, magnesium would be +2, and they all have the same, well, they have the same configuration as neon, which makes them more stable as ions because of that valence shell of electrons. All right, so F minus 9 plus 1, 10 electrons in the configuration. Sodium 11 minus 1, 10 electrons in this configuration, and then neon has 10. So anyway, metal ions. This is zinc, and so if I look at zinc's structure, all right. Oh, I must have done that with this button right here because I was holding the cap up against it. I'm not very good at using this for that. So, interestingly enough, when we're talking about zinc, and zinc makes a +2 ion, it doesn't do it like sodium and magnesium do, okay? It does something different in that because it's more stable to have a full orbital in terms of the d orbital. It's better for it to be full than having electrons in it and have the s orbital go away to remove those two to make zinc +2. So it changes and you lose the s orbital. And so because they're very close to the same energy and the stability is better without the s and with the d being full. Okay, so for charges greater than +2, additional electrons are then lost from the d orbital. So try this with iron. Okay, try this with iron, which is right here, and a half full valence shell is more stable than in this case, and so that's what you're going to work with, and use zinc as your model. I think it's easier to write the neutral first and then make the decision. Yep. Yeah, yeah, so, well, you're taking your, with those, yeah, it's always on the Roman numerals, always on the metals, and so that's +2, +3, and so it's telling you the charge, and so, you know, and that's, so that translates to that being the ion. You know, sometimes it says like iron 3 chloride, and so then it would be just telling you that it'd be FeCl3. Because the charge, if it were FeCl2, then it would be the Fe2 version. And so you, yeah, it's always telling you how many electrons are gone from that, yeah. That's an interesting way to look at it. I've never heard it from that perspective, but yes,
I
that's
was
true.
just sitting here thinking.
This is looking for S1. I think that's the way those feel. See how I do? No, if it left it, this is 6. I think that this would be more stable, my opinion, but I think I'd have to go back and look at that. So does it even take an old chemist practice? Yeah, I've been doing this. I don't do these very often on larger molecules, right? And so, anyway. Electron configurations. Fun stuff. All right, you guys think you can do that?
So why isn't before X learning before S?
Because this is what these have a tendency to do this instead of keeping the S, they reform and use the d orbital instead of that s orbital, even though in terms of the fill order we filled the s first.
Okay.
Even because they're very close to the same energies. And so putting those electrons over into the d is more stable for the atom. And so that's the way I understand it, yeah. Okay. And so we're showing you that happens. And then sometimes we get a partial, like an S1 in that situation. And then a D will be half. And I thought with the Fe2, for some reason, it was the 4s1d5 was more stable to put those single electrons in each of the lobes. And I was thinking that was a more stable conformation. That's not what this textbook is saying, but, and like I said, I'll have to go back and look at that. Because I know that sometimes we do that. But it's been a long time since I had advanced inorganic chemistry. 24 years, 25 years since I was in that class. And I don't teach it now, so yeah. Some of that goes to the wayside. You forget those telephone numbers and passcodes that you don't use, right? Yeah. All right. Quantum numbers. Whole nother fun part of chemistry. I want you to make this easier for you, okay? And I'm going to do my best to simplify this. In this class, we don't have to do any calculations. We just have to learn how to label quantum numbers. We're introducing language right now, so that if you go on, this is a majors course, and so when you go on and take physical chemistry, then you've had an introduction to the language, okay? And how to choose what you're going to use for quantum numbers. And so there's a principal quantum number, an angular quantum number, a magnetic quantum number, and a spin quantum number. Okay? Those are 4 things we're going to talk about. They are all connected. okay? There are rules that go with this when we're doing quantum numbers, all right? Now, the first rule is integers. The principal quantum number is whole counting numbers, and right up here we go to, 7. Okay? So, you guys can count to 7, right? So I could be n equals 1, or n equals 2, or n equals 3, or n equals 4. You with me? I can only be one of those. Okay? So whatever it is defined as, I've got an n. Okay? Positive values, and you guys can count to 7. All right. Now, the next one, the angular momentum. The angular momentum. It has set values also. Okay, you guys with me? And those values are n minus 1. So if my quantum number, principal quantum number n is 1, right? What's my L value? It's 0. If it's 2, what's my L value? It's 1. You guys can do 7 minus 1, can't you? Okay? I just defined all the possibilities. You guys with me? So it can be, well, 0 for S, 1 for P, 2 for D, 3 for F. N minus 1. Okay? Loud values, L depends on N, and those values range from S to F. Those are the subshells. It stops at the F because we can't go beyond there because we don't have g orbitals and those types of things. Well, it would be 3. I have to look at that. We'll get there. Okay. All right. The first two quantum numbers for an electron are 3 and L equals 2. Which energy and subshell does that electron occupy? 3 and L equals 2. So the third energy level in the subshell is L equals 2. SPD. So that's the third one is D. That's a 2. And so it's going to be a 3D subshell. 3D subshell. Subshell, and we can't go past F because we don't have orbitals. Theoretically, we have orbitals past F, but we only go to 3 on that. Okay. The magnetic number. Okay. So if I have a magnetic quantum number M, when L equals 0, the subshell is S. And for one orbital, the M value is 0. Okay? When I get to P, all right, when I get to P, I have PX, PY, and PZ, right? You guys with me? Three values, -1, 0, and +1. Okay? So those are the positions that we would establish here. There are 3 values. If I move to D, right, then we need 5. Right? So it's going to be -2, -1, 0, +1, and +2. If I go to 14, or go to 7, excuse me, 14 electrons. If I go to 7, then I would have -3, -2, -1, 0, +1, +2, +3. 7 total numbers. 7 total numbers. And then the last one, right? Hang on, let's just do it real quick. There's two possibilities for it, plus 1/2 or minus 1/2. It has to be one or the other. Okay? Now this is actually defining the spin on the electron within the orbital. Now what do we know about the spin of the two electrons in one orbital? One's got to go up, plus 1/2. One's got to go down, minus 1/2. You want to define it that way, right? You with me? So those are the two possibilities. Now, what we're doing with this is in an atom, no electron can have exactly the same set of quantum numbers. No two electrons can have the exact same quantum numbers. All right, you guys with me? In other words, each electron is defined by this set of numbers. And then we can take these, plug them into a wave function, and calculate energies and those types of things. And so, anyway, which subshell is indicated by L2, and what are the M sub L values allowed? So what is L equals 2? So that's a P subshell. 0 is S, 1 is P, 2 is D. Right? Isn't that right? Yeah. So that's a D orbital. And so that means that we have what? -2, -1, 0, +1, +2. Okay? Yeah, it's coming back from high school, right? So, we've done quantum numbers for general chemistry now. Yeah, you're saying what? Okay. Can you count to 7? Yeah. Then can you go from 0 to 3? Yeah. And then can you take that 2 and get 5, or that 3 and get 7 subshells, M sub L's? Okay? Literally, that's it. This isn't, it's just a little like simple puzzle. Okay? I know it seems confusing, but let's go back to the beginning one time. Okay? What principal numbers, principal quantum number N? What are my choices? 1 to whatever our highest energy level is, right? Literally, that's what it would be. And then angular momentum, right? What is it? What are the values? N -1, right? Yeah. Go into that orbital, SPD, and F. The magnetic quantum number, what is it? It could be 0 for S, -1 to +1 for D, -2 to +2 for, I said P was the first one, 3 orbitals, then 5 orbitals for D, and then -3 to +3 for F. Okay? That's it. That's the only options. Okay? And then on the last option, what are the last 2 for the magnetic spin number? The spin number. +1/2 or -1/2. The only 2 choices. Okay? So, not a lot of choices, right? You guys with me? It's just identifying. Now, the type of question that your author likes to use for these are this type of question, where which of these are valid? Identify the energy level and sublevel of any of the following sets that are quantum numbers that are valid. Why is this A not valid? What's the most obvious thing that pops right out? The spin number, it's what? It's 0. Can it be a 0? No, +1/2 or minus 1/2, right? And so for energy level 1 and L equals 0, what orbital are we talking about with L equals 0? S, okay, you guys with me? And so is M sub L valid? A 0 on the M sub L. Yeah, because that's the one option that we could have there, okay? So if I'm looking at the energy level 2, and we're talking about L0, then 0 is an S orbital, right? 2 energy level S, and I could have M sub L being 0 and a minus 1/2. That is a valid set of quantum numbers. Okay? If I had the second electron in this sublevel, the second electron, and I put it in there, how would this line change? There'd be one change in that line. If I have that second 2s orbital, what would it be? The half would change to positive, right? And then I have those 2 electrons in the same energy level that are paired. The plus 1/2 and the minus 1/2. You guys with me? Right? So if I'm moving to the next one, the third energy level, a 1, that means it's a p orbital, so 3p, right? And that's valid because it's a 1, and then a 1/2, that's valid. That is an electron that exists. If I move to the last one, notice I've got some minuses right here. On that L is the one that sticks out because those are all whole numbers, okay? Positive whole numbers. Right, so that's kind of how we would look at that. I'm out of time, so I'll quit there. That's why I skipped a couple slides. I'll have to back up and we'll review all of that next time.